Hi, I'm Hanchen, and so today we're going to talk about one of our recent work using 3D geometry to pre-train molecular graph representations. We name our work called GraphMVP, so which stands for multi-view pre-training. So here multi-view means 2D and 3D molecular graphs. And this is the joint work with Sheng Chao, myself, and Wei Yang, Zhong, Hongyuan Jian. It is published in ICR this year and presented at a few more workshops as well. Okay, so we can start from the very beginning. We can start from the intro of representation learning. So we know that modern machine learning is based on learning meaningful representations, usually with deep neural networks. So a generic pipeline is shown in the slide. So here the input of the neural network model is the image. And after, let's say, a stack of, well, here we say convolutional layers. Maybe nowadays it's transformers or graph layers, but essentially we will get some representations. So here we use RD to represent d-dimensional vector to represent the image. And then we can train, let's say, a linear classifier or some other shallow linear-like structures or models to serve as a classification or regression tasks. And so this is basically the general idea of representation learning. So why we need to learn useful representations. And to learn useful representations, a famous or recent popular technique is self-supervised learning. And it usually forms like a two steps paradigm. So we first pre-train the model or pre-train the feature encoder, representation encoder based on a large scale on labeled data. And then we fine tune the pre-trained models on some usually small downstream supervised tasks. And the pre-training usually relies on label-free proxy tasks, such as it can be further classified of either generative or discriminative pre-training objectives. And for instance, let's say for generative, a famous example is we call image impeding. So the idea is like we use we randomly crop a certain region, maybe the central region of the image, and then we train the network, learn the representation of the image, and learn to restore the missing parts. And this is, of course, you know, it don't require like any human annotations. So it's unsupervised, it's self-supervised. And a famous example in recent years for discriminative pre-training or contrastive pre-training is we call it contrastive learning or contrastive racial representation learning. So it is shown on the right diagram. So essentially, you input you augmented the image with a few augmentation techniques such as random cropping or such as grayscaling, and you input such augmented images into the same CNN, into the same feature encoder, and you hope and you use a few contrastive based laws to let the network learn the similar, the image from the same, the augmentations from the same image to be similar, and the augmentation from different images to be different, to be compatible with each other. So essentially, it's instance discriminative tasks, and it is known as contrastive learning. And the fine-tuning is usually we fine-tune the pre-trained model with labeled downstream data sets. So here we mean like we fine-tune the pre-trained graph neural network models on some specific like biochemistry or biophysics data sets. And speaking of self-supervised learning on graphs, or more specifically on molecule graphs, there are also some notable works in the recent years. So a few notable examples is like the first is GPT-GNN. It's a generative pre-training. So it's kind of we randomly masked a partial attributes or edges of the graph, and we train the network learn to complete them. And a contrastive-based methods example is called GraphCL. It's basically you augmented the graph with, let's say, edge dropping or edge perturbations or node dropping, and then you train the embeddings to be similar, or the projected embeddings to be the similar. And in the work, we have also compared GraphMVP with a bunch of other 2D graph SSL works, and we provide a conclusive summary in the appendix of our work. So before GraphMVP, there's not much work that using the 3D information of the molecule graphs for self-supervised pre-training graph neural networks. Okay, our motivation is very simple. It's basically, we can say, we think or intuitively, or we should 3D molecule information will help the representation learning process using self-supervised pre-training. So our revisions are, so first, 3D information or 3D structures of the molecules will provide some complementary information with its original representation, which is only a 2D connectivity graph. And it is relatively expensive or relatively unusual to have for a lot of molecule graph data sets, such as molecule net, Campbell, or zinc. But it is emerging. So there's a lot of researchers have noticed that, and they have started to create a large collection of the 3D molecule structures, such as genome, such as atom 3D and molecule 3D. So the below we show the diagram where you can see where the 2D molecule graph is showing that the diameter of the graph is large, but essentially in spatial distribution, they will provide. You can see the 3D structure will provide more information with respect to its 2D connectivity representations, either from the diameter or from the donor acceptor structure predictions. Yeah, so the overview of a method is very simple. Yeah, we name our method called GraphMVP. It stands for multi-view pre-training, and the 2 stages. So we pre-train the graph neural network, both 2D and 3D, on a large scale molecule graphs, where both 2D and 3D structures are available. And then we fine tune on the downstream data sets where only 2D molecule graphs are available. Yeah. And there's 3 parts of our training objective. The first part of training objective is called contrastive self-supervised learning between the 2D and 3D views of the molecules. And so the main idea of contrastive self-supervised learning is to first define the positive and negative pairs of views from an inter-data level, and then to align the positive pairs and contrast the negative pairs at the same time. So for each molecule, we first extract the representations from the 2D and 3D views. And as shown in the image, the blue vector and the red, or not red, but you know, the other embeddings. And then we create a positive and negative pairs for contrastive learning. So the 2D, 3D pairs in this image, since they are from the same molecules, they are treated as positive. And if they're not from the same molecules, they are treated as negative pairs. And then we use align positive pairs and contrast negative ones. And there's a few various ways that we all few various laws formulations that we can choose for contrastive learning. And in the paper, we stick to the either the info NCE or the EBM NCE. They have different formulations and different physical interpretations. So for the details, please check the papers and the relevant literature as well. And the second part of the training objective is we call a generative self-supervised loss between the 2D and the 3D views of the molecules. And a generative self-supervised learning is also a classic track for unsupervised, self-supervised pre-training. And it aims at to learning an effective representation by self-reconstructing each data point. So a famous example is we can see autoencoder or variation autoencoder. Yeah. So specifically to molecules, we have one 2D graph and maybe a certain or multiple 3D graph corresponding to different conformation structures. So our goal is try to learn a robust representation that can from 2D representation that can recover its 3D counterparts, or from the 3D counterparts that can reconstruct or recover its 2D parts. So by doing so, a generative self-supervised learning can enforce the both 2D and 3D graph neural network to encode the most crucial parts, the most crucial geometry or topology of the molecule graphs, which we believe or which are usually be able to be benefit for improving downstream performance. So there are many options for generative models, such as VAE, as we said, or GANs or flow-based models. So in GraphMVP, we prefer a VAE-like method because the following reasons. The first reason is like the mapping between the two molecule views is with randomness, is stochastic, since multiple 3D conformers will corresponding to the same 2D graph topology. Second reason is an explicit 2D graph representation, like the feature encoder, is required for transfer learning or for fine-tuning on downstream tasks. And the third reason, last reason, is the decoder for the structured data, such as graph, such as molecule graph, are often highly non-trivial or hard to define in comparison with, let's say, image decoder or image generation pipeline. So which will make it as a suboptimal choice. Yeah. And this is the reason we stick to the VE-like loss, but not from on the data space, but instead of on the representation space. So we name this new type of loss called variational molecular reconstructions. So for the details and mathematical deviations of this loss, please see our papers and the main context and the appendix. And the last part of the GraphMVP loss is basically the self-supervised loss between the 2D and 2D views. So this is so empirically we find that to further incorporate these parts of loss will further increase the performance of your pre-training, the performance of your model. So essentially, in addition to using the both contrastive and generative loss between 2D and 3D views, we use the third part, which is either the generative or contrastive SSL between the 2D and 2D views. We find it's helpful. Okay, so yeah, so make a slight summary is makes a slight summary on the three parts of the GraphMVP. So we observe that adding or combining or simple combining the contrastive and generative SSL laws or SSL objectives is beneficial. So which we think which might because they're complementary for the representation learning tasks. So we provide some intuitive explanation for that. So let's say from the representation learning perspectives, contrastive self-supervised learning is on the inter-data level, or so it's focused on the relationship between different data points, and the generative SSL is intra-data level, so it's more likely to learn the data distributions of the data points itself. And from the distribution learning perspective, contrastive SSL is doing distribution learning in a local level, while the generative SSL is doing it in a global level. So intuitively, we can see that they are complementary. So it might give us an explanation why combining two parts of self-supervised learning objectives is helpful. And speaking of the experiments, so we pre-train the model. We pre-train the model on the genome with 50K molecules, and each molecule have 5 conformers. It's a fixed number, and it's based on our it is based on our ablation studies. And for downstream fine-tuning, we mainly investigate 2 downstream tasks: property prediction and drug target interactions. Okay. So bear with me with the wrong references. So for the backbone models, we use the 2D gene versus gene, the graph isomorphic network, and its first is published by Xu, Köhler et al. In ICLR 2019, and it is further modified by Hu et al. From Stanford the year after. So they have modified some modules for the edge message parsing part. And for the 3D GNN, we use SHNet. It is published by a group of researchers from Technical University of Munich, and it turns out that it's a quite robust 3D molecule graph encoder. And in the table, we summarize the statistics of the downstream data sets. And for the results, for the main results of this paper is based on the molecule property predictions. So as we can see that incorporating 3D informations, GraphMVP and its variations has achieved, well, let's say in general, the best performance in combination with all the previous self-supervised molecule graph learning that is only based on the 2D graphs. So which have also empirically validate our idea is that using 3D geometry, using 3D structure information will help the self-supervised learning on the molecule graphs. And and we also provide more results from larger data sets rather than the 8 data sets from MoleculeNet, and also some drug target affinity predictions, which is regression tasks. And we report the mean square error using various runs, of course, averaged over various runs using scaffold splitting. And we can see that GraphMVP has also achieved the best performance in combination with its previous baselines. For sure, nowadays there's some follow-up works, and some of them has achieved better scores on these tasks. Okay, and the last part of the result section is ablations. So we do some ablations on changing the masking ratios, which is the one we use in the generative self-supervised learning. And we also try to change the number of the conformers we use for pre-training. And it turns out using more conformers does not always help. And also using more conformers will introduce more computation cost. And we also try doing some ablations on the objective functions. What if we only use the first part? What if we only use second parts? And for the first contrastive SSL, what if we use info NC? What if we use EBM NC? It looks like, and the detailed descriptions can be found in the paper. Okay, and speak for the future directions and some related works. So there's some simultaneous work with GraphMVP, which is called 3D Informatics, which is also focused on the 2D and 3D joint self-supervised learning, self-supervised pre-training. And it is developed by Hanchen et al. And published in ICML conference this year, later this year. And there's some emerging works just to focus on the large scale 3D molecule self-supervised pre-training, like Unimode or pre-training while denoising for molecule property predictions. And there's some other works like recently developed by also me and Shengchao and a few others. We kind of use probe models to evaluate what kind of knowledge is transferred in this self-supervised molecule representations. There's still a few open questions that is not answered, such as, can we have a better theoretical explanation, theoretical understanding of why the different self-supervised learning are, let's say, complementary or can help with each other? Yeah, is there a better framework to unify the contrastive and generative self-supervised learning? Yeah, we tried in GraphMVP, we tried use maximize mutual information to explain, but we didn't find a good interpretations for that. And I think there's a lot of people are working on using multimodal, which is we use graph representations and smiles representations or language representations to train a multimodal foundation models for molecule graphs, because it has been shown very successful in visual language models, and people are thinking about, can we use it for molecule graphs, for molecule representations as well. And there's some other direction like knowledge distillation. For instance, UNITE is a very famous work, it's recently published in accepted in PNAS, and essentially it is using a lot of quantum chemistry methods to calculate the atomic and molecular orbitals as your input feature. And they have shown that with such comprehensive features as an input, just using a very simple graph neural network will help you to achieve the best performance on datasets such as QMNI. And can we use the distillation to distill the knowledge from these methods to the original 2D graph or 3D graph neural networks, since we don't want to use a very we want to use a computation effective way to do the training. And yeah, that's all for today. Thanks for listening.